Hello and welcome back. We are finishing section 2.2.2 about the vector form equation of the plane, and in this video we are going to do example 2.2.4 and example 2.2.5. So let's go ahead and start with example 2.2.4, and we're told that we have a plane pi which is given in vector form. X, y, z is equal to 2, 3, minus 1 plus s times 1 minus 1, 3 plus t times 2, 0, 1 for s and t in R. And we're asked to give a general form equation for the plane out of this vector form equation. So the first thing we might do is remind ourselves what the general form equation looks like. Ax plus by plus cz plus d equals 0. And then let's take stock of what we have and what we need. So if we make a little sketch of a plane here, we need to give the general equation, which means that we need a normal vector, which is the a, b, and c that we see in the coefficients of the general form equation. We are given the vector form, so we have to remember how to interpret that. We see a point in the plane. We see the point 2, 3, minus 1, and we are also able to see two vectors in the plane or parallel to the plane. So let me sketch those in. We can see vector 1, minus 1, 3, and vector, let's draw it here, 2, 0, 1. So out of that information, we have to give the general equation. And so the first thing that we'll probably want to do is create our normal vector. And we can see we have two lovely vectors in the plane. A cross product will take care of that for us. So we are going to let the normal vector be the cross product of these vectors. So 2, 0, 1 crossed with 1, minus 1, 3. And so I'll recopy them here going down, 2, 0, 1, recopy the first two, 1, minus 1, 3, 1, minus 1, bar out the first line, and we've got here, so 0 minus minus 1 is going to give me 1. 1 minus 2 times 3 is 6. That is going to give me minus 5. And minus 2 times, or minus 0, so I get just minus 2. So there's our normal vector. There is our a, b, and c. So if we go back in this equation, ax plus by plus cz plus d equals 0, then we're looking at 1x minus 5y minus 2z plus d is 0, and this is something that we've done before. To find the d, we are going to plug in the known point that we have in the plane, so 2, 3, minus 1, and so we're going to get 2 minus 5 times 3 minus 2 times minus 1 plus d is 0, and so what is this now? 2 minus 15 plus 2 plus d is equal to 0, so d is 11. And so we can give our equation as x minus 5y minus 2z plus 11 equals 0, or you can move that 11 over to the other side to minus 11 if you want to. So there's example 2.2.4. Now going on, example 2.2.5, we're going the other direction. This time we are given a plane in general form, and we want the vector form. So we are given this. And again, a little sketch, always recommended. We're given that we can take a normal vector as the vector I can read off of the coefficients, the vector 1, 1, 2. And we need to find both a point in the plane and two vectors in the plane to be able to give the vector form equation. Well, finding a point in the plane we've done before. We've done it by choosing, right? We just choose values for two entries, for two variables, and solve for the third. So let's let y and z be 0. How about that? Make our lives easy. That's going to tell us that x equals 3. We're actually finding the intercept, the x-intercept of this plane. That's not important to know, but incidentally that's what we're doing. So we've got a point 3, 0, 0 that's on our plane. Now, we need to find two vectors. We need to find two vectors of the form, let's say, p, q, and r that are in the plane. And if they are in the plane, then when we dot them with the normal vector, they should give us 0. So that is actually giving us another little relationship here. P plus Q plus 2R has to be 0. And so we're going to do the exact same thing that we just did. We're going to make choices, and then we're going to solve for the remaining P, Q, or whatever R. But we're going to do it twice. We're going to do it twice because we need two different vectors. So let's first start and say, well, let's let Q equal 0 and R equal 1. For example, any choice will do. If I do that, I'm going to have P plus 2 equals 0, or P has to be minus 2, which is telling me that the vector 2, 0, 1 is parallel to the plane, or is in the plane. Well, I need a second vector, so let's make other choices for those letters. And so let's say, well, how about this time Q equals 1 and R equals 0? Well, that's going to tell me that P has to be minus 1, and in other words, the vector minus 1, 1, 0 is also in the plane. Well, now that I've got a point in the plane and two vectors parallel to the plane, I can write the vector form equation. The position vector x, y, z of any point in the plane can be written as the position vector of 3, 0, 0 plus some multiple of the first vector that we found plus another multiple of the second vector that we found for any s and t in R. And so there is one valid expression. There are many, many, many others, depending on the choices that one makes to find points in vectors. But there is one valid expression of the vector form equation for our plane pi.